Hi, everyone. Welcome to online lecture 5. This is actually one of the lectures I really like because I think it's suggests some designs that are more realistic for folks in the psychological and epidemiological fields, but it's more realistic to us. It's a beautiful thing to be able to do a randomized clinical trial, but it's not necessarily always realistic. So I'm looking forward to sharing some of these other designs with you. Anyhow, the reading is chapter 6 and 7. Okay. And let's start off by just reminding ourselves of the experimental, which is, often a randomized clinical trial, a randomized trial, where you have your population, you do a random allocation to group, you pull a sample actually, hopefully randomly, and then from your sample, you do a random allocation to group A and group B. And in an observational cohort study, which is the first kind of study we're going to talk about today, you have a population and they go to group A and group after you pull your sample again, hopefully randomly, maybe not. They go other than randomly to group A and group B. Okay, so we're going to actually talk about cohort studies, followed by case control studies, followed by cross-sectional studies, and then I'll say a super brief word about correlational studies. Okay. So once again, I am sharing some Hopkins-Bloomberg slides with you. I really like these. I, of course, include the names so you know who gets credit. I hope you enjoy them as well. Okay. So let's start with the design of a cohort study. So you start with a defined population, okay? And again, this should talk about, that's okay. So from our defined population, what we're going to do is non-randomly, we're going to identify exposed people and not exposed people. Okay, so let's say our exposure in this case is cigarette smoking. Could be anything, but let's call it cigarette smoking. Then we look at those people who smoke cigarettes, we look at those people who do not smoke cigarettes, and I mean, we could decide whether we want to include vaping with these groups or not. That would be kind of an important design decision. Probably would impact our study later on, but for now, let's just keep it simple and let's just talk about the cigarette smoking. And then we're going to look at people who develop coronary heart disease or not. Okay, so we're going to have to wait a while because we're choosing them at the point before the disease onset. So we're going to have to wait and see who develops the disease, who does not develop the disease in both groups. Okay. So there is a prospective cohort study, which is a concurrent cohort study or longitudinal study. And if you can't do that, sometimes people do what's called a retrospective cohort study, a non-concurrent cohort or historical cohort study. So I'm going to first, the one I was just talking about was the prospective, and I'm going to walk you through that, and then I'll walk you through the retrospective. Okay. So let's start with a prospective study. Okay, so the study starts in 2000, and here's the investigator right here, starting right here. And just like we saw on the previous slide, we have our defined population. From there, we pull our exposed and not exposed groups, our cigarette smokers, our non-cigarette smokers. Now, I am pushing past the how we're pulling the sample, and there's a reason for that. It's because that is not necessarily a big part of this design. So I'm really focusing more on how we assign people to groups once we have our sample. Okay, so in a non-randomized way, of course, because we're not going to tell you guys got to start smoking cigarettes and you have to stop. That's not realistic. So we're just looking at people who naturally smoke, who naturally do not smoke. And then so we pull them at the beginning, we look for the exposure, and then we look for the disease outcome. Okay. All right. So if you might imagine, if you really wanted to do a true prospective study, maybe you start with 10-year-olds who are unlikely, I think, unlikely to be smoking at that age. And then look for who becomes exposed and not exposed, look who develops the smoking habit and who does not. And then much later on in life, you're going to look for the disease and no disease. So you might be thinking, wow, that's a very long time, and you're absolutely right. So maybe you might want to consider a retrospective study. Now here you get to start at the disease part. So you can pull people who already have coronary heart disease and do not. So you're starting here in the year 2000. And then you're looking backwards to see who our exposed and not exposed groups were. Now, this can be, we'll talk about case control in a little while, and I just want to be clear that even though we're starting here, this is still considered a retrospective cohort study because of the direction we're looking at it. Okay. All right. So prospective cohort study, the investigator starts the study from the beginning with the identification of the population and the exposure status, exposed, not exposed groups. Follow them over time for the development of the disease. This takes a very long time, or a relatively long time, I guess, to complete the study, as long as the length of the study. Okay. Whereas a retrospective cohort study uses existing data collected in the past to identify the population and the exposure status, and then determines at present the development status of the disease. Okay, so we're using historical data to see the exposure status, and then we determine now what the status is of the disease. This one's nice because you spend a relatively short time to assemble the study population and the exposed, not exposed groups from the past data, and you determine the disease status at the present time, so there's no future follow-up. Okay. Now, there is something called a combined prospective and retrospective cohort study. In this case, the investigator uses existing data collected in the past to identify the population and the exposure status, but then follows them into the future for the development of the disease. So you don't have to start them all the way back from the beginning. You're using historical data to identify that, but you are following them to see the development of the disease. So this is also nice because you spend a relatively short time to assemble the study population and the exposed, not exposed groups from past data, but you are going to spend the additional time following them into the future for the development of the disease. This is a little bit cleaner than the retrospective cohort study, in my opinion, but again, it takes more time. So actually, before I move forward and talk to you about biases, let me just show you, if we're doing our little person guy, he would be like right around here. So using historical data to get the exposed, non-exposed status, but still waiting for the development of the disease. Okay, so I just wanted to point that out. Okay, so now let's talk about some types of bias that can happen. So selection bias, if you select participants into the exposed and not exposed groups based on some characteristics that may affect the outcome. How can this happen? So for example, let's say you are selecting the exposed and not exposed groups based on, you're finding them based on health records. Okay, so it might be that you'll see more common for one person to actually visit the doctor than others, for one group to visit the doctor than others. So you could get a little foul up there. Information bias. Collect different quality and extent of information from the exposed and not exposed groups. Okay. So this can happen when you have a loss to follow-up that differs between the exposed and not exposed groups, or between the disease and no disease. Right? Loss to follow can be a big issue, and it can be a big differential issue. Okay. So, and collecting of different quality and extent of information, I mean, that can be caused due to loss of follow-up if you don't have them, but it can also be that sometimes there's less information available for one group than the other. Or even a collection error. Okay. And then finally, misclassification bias. You can misclassify exposure status or disease status. That can happen. It's a little bit less likely with something like smoking and coronary heart disease. But certainly, sometimes it can be a little bit less clear what you're identifying. Okay. Certainly in psychology, I'm sure you can imagine that sometimes it might be a little less clear to identify if someone had a true major depressive disorder in the past. Let's say you're doing either a retrospective or a combined retrospective and prospective one, and you're trying to identify depression in the past. As you might imagine, that can be a challenge. So you might misclassify. Okay. So let's look at this. When is a cohort study warranted? Well, when the alleged exposure is known. So you have to know what exposure you're trying to study. When the exposure is rare and incidence of disease among exposed is high. Now, it's not so much that the exposure has to be rare, but if the exposure is rare, but you have a high likelihood of the disease within the exposed group, then this is actually a good choice. Okay. And when the time between the exposure and the disease is relatively short. Now, that's nice too, because you don't want to wait decades for them to develop the disease, because, again, that's just a lot of time in a single study. And then when adequate funding is available, since it probably will take a while for you to complete the study, and when the investigator has a long life expectancy, which is just to show you that epidemiologists do have a sense of humor. Again, because it'll take a long time to run a study, right? Especially if you're doing a prospective one. Okay. So that's a little bit of an introduction into cohort studies. I now want to turn your attention to case control studies. Okay. So let's look at a case control study. Now, this is a little bit different because the arrows are going the opposite way. So we're starting with disease, no disease, and then we're looking for the exposure. Now, this is the one I was a little concerned might be confusing with the retrospective one, because it kind of looks like in both places we're sort of starting at the same place. But remember, with the retrospective, we are maybe starting in time here, down here, right? But we are looking for the exposure first and then going down to disease. Here, we're looking for disease status first and then looking for the exposure. Why does that matter? It has to do with, again, what we were just talking about. If the rate is rare in an exposed group, it's going to be harder to find it in a case control than in a retrospective cohort. It's going to be harder to find the right people. Okay, so we'll talk more about it in a minute, but let me put that little bit of a preview in your mind. Okay, so again, this can be the same sort of study. We can start with people with coronary heart disease and no coronary heart disease, and then go backwards and figure out if they engaged in cigarette smoking and how much and how often and all that kind of stuff to decide if they're in the exposed or not exposed group. Okay. And I've been leading with that example because that's what we have right here. So here we have our cases with coronary heart disease, our controls without the disease. And then we look back and we see who smoked cigarettes in each group and who did not. And we can see that in our coronary heart disease group, there's a higher percent that smoke cigarettes than in the controls. We don't know if this is a significant difference. We're not going to worry about that for right now, or probably not really in this course. So we're going to worry too much about that, but it gives you a good sense for what's going on. Okay. Now, here's an interesting point. Sometimes it's hard to find cases for any study, right? Sometimes it's just hard to identify those people with the disease. So to increase your power, sometimes people will do something like have 2 controls per case or 4 controls per case. And you can do a power analysis to figure out what might best suit you if it's easier to find your controls than cases. However, as a general rule, you don't tend to go higher than 4 controls per case. There's some point where it stops being helpful to your study and to your power. So you might think about this kind of design. This could be helpful to you, okay, for a dissertation or for studying in general, if this is your situation. Okay. Okay, so now we ask the question, when is a case control study warranted? Now, you might conduct a case control study before a cohort or an experimental study to identify the possible etiology of the disease. Why? Because it costs relatively less and can be conducted in a shorter period of time. Okay. So let's think about something that's a little bit more psych related. I suggested the notion of depression as an exposure, and let's look at the disease as suicidology. Okay. So let's say, we weren't really 100% sure that depression is our main, the main exposure that we wanted to study in this case. Maybe we want to study, we're not sure, like maybe it is depression, maybe it's overall symptomatology, maybe it's something else. Okay, so I'm just throwing that out there. And so we might do a case control. Okay. So it costs relatively less, can be conducted in a short period of time. Also, for a given disease, a case control study can investigate multiple exposures when the real exposure is not known. That's really nice. Think about that, right? So where our case control study is about suicidology, and we can look at multiple exposures. We can look at depression. We can look at anxiety. We can look at post-traumatic stress disorder. Okay. Now here, this is with the rare thing again. So a case control study is preferred when the disease is rare. Remember last time it was when the exposure was rare. Now it's when the disease is rare, because the researchers can intentionally search for the cases. Okay, so that's the idea. A cohort study of rare disease would need to start with a large number of exposed people to get adequate number of cases. That's why you wanted the incidence high in the cohort study, because you can at the beginning get your group of exposed people for the cohort study, right? But if you're going to get these exposed people, you want, so to speak, I mean, research-wise, you want a high incidence of the disease so that you can see what happens. Here, you're starting at the disease level. You want to make sure that if the disease is rare, again, you can get a lot of cases as long as you can look backwards to the exposure. Okay. Okay. Let's talk about some issues in the selection of cases. Cases should be as homogeneous as possible. So you want to have a very good definition of cases. You want it to be well formulated, documented. If diagnostic tests are used to identify cases, you want high sensitivity test. So what does that mean? We haven't really talked much about sensitivity and specificity at this point, but it is an interesting issue with measures. And a high sensitivity case is how likely is it to be able to find your positive cases? That's the best way I can put it for now. Okay, how likely is it for you to be able to find your positive cases? Okay. Low sensitivity cases, low sensitivity tests, and thus high specificity will result in, okay. So, yeah, okay. They're going a little bit deeper with this, sorry. Let me rephrase this for you. So high sensitivity tests are how well it can identify your cases, right? How much positive cases it's going to pull. But a high sensitivity test is also going to yield a high number of false positives. You see, it's pulling more people into your positive bucket. So some of them are going to be wrong. Low sensitivity case, if you use restrictive criteria, then it'll have high specificity, which is good at identifying negatives, and then you'll have less false positives. Okay, so that's kind of true. You can have a high sensitivity, high specificity test, which is ideal. But you wanna make sure, I mean, if you have to choose between these, you wanna make sure that you don't have too many false positives. Again, that's misclassifying of cases that we were talking about before with the cohort study. So you want your cases to really be as tight as possible. Okay. So what about a mild form of the disease? If you include it, it may make a lot of higher false positives than a severe form of disease. So if we're looking at major depressive disorder again, do we want to be, we might want to be really strict, really tight, make it relatively a moderate or severe case of major depressive disorder. Oh, I'm sorry. For our case, we're looking at suicidology. So I'm sorry. So you might want to look at high, a high or moderate case of suicidology there for your case, and then you can go back and look at your exposure of major depressive disorder. So sorry about that. Okay. What about incident cases? Now, that means newly diagnosed. They may be harder to come by, but they're closer in time to the exposure. And unlike prevalent cases, they are not likely the survivors of the disease. Now, again, this is a little bit of an epidemiology concept, but we often talk about survival and mortality in epidemiology a little bit more than in psychology. But think about it this way. If you have a case that's been diagnosed a long time ago, then what is so someone who has a high rating or high self-report suicidology, but they're still thankfully with us, what does that mean? They're likely a survivor of the disease. So incident cases, we don't know because it's new. Okay. So again, if cases are misclassified, including false positives, the findings may be false. So just all stuff you want to think about if you're doing this case control study. Okay. Now, controls. Control should come from the same population at risk of disease from which the case is developed. But practically, controls are often selected to be similar to cases on key factors, but without the disease, because it's difficult to define the population at risk of disease. So different types of controls may be used and they have different limitations. So let's think about it. If we're looking at high suicidology, we want them to come from the same population at risk of disease. But we may not know exactly what that is. So instead, we might choose people, okay, so let's make sure we're choosing people who are similar in age, in gender, um, in environment, in historical factors, right? Maybe history of abuse, for example. Okay. So let's talk about some different kinds of controls that we can have. Hospital controls, for example. They have a similar quality of information and are convenient to select, but they may have characteristics or diseases that led to the hospitalization. So let's go back for just a moment to our coronary heart disease and smoking example. Okay, so we're looking at coronary heart disease. So if we take hospital controls, what's really nice is we're going to get some really good information, right? Convenient. But again, maybe they have other diseases going on that led to their hospitalization. So that could be a bit of an issue. Dead controls. If cases are dead, information of past exposures will be given by surrogates such as spouse, children, and so dead controls share the same limitation. Okay. Best friend or neighbor controls. Maybe they share similar characteristics. Maybe they're too similar. And population controls. If you want to do a population control, random digit dialing is kind of an old way to do it, although that probably is still sometimes used. But you might dig into the population in some other way to try and get at people who could be from the population who could serve as a control. Okay. So let's talk through now some other issues involved with case control studies. Matching. Matching is the process of selecting controls in a case control study so that the controls are similar to the cases with regard to certain key characteristics such as age, sex, and race. Matching can be performed at an individual or group level. Okay. So if we individually match, we kind of talked about this before with the idea of match pairs. So everyone in the case group, so if you pick person, you have person A in the case group, okay? John Smith. John Smith is a male who is 65 years old and Caucasian. So now in your control group, what you want is a male 65-year-old person who's Caucasian. Okay. Group matching. Now this is a little bit easier because you just need to make sure that on a whole your groups match up. So if I have a split of 40% male, 40% female, 20% non-binary, then in my case group, then that's what I want in my control group. Okay. Let's talk through an example. In a study of breast cancer and reproductive risk factors from the New Mexico Women's Health Study, controls were ascertained using random digit dialing with frequency matching on ethnicity. The three age groups, 30 to 39, 40 to 64, 65 to 74, and the 7 health planning districts. Okay, so we're just making sure that we're matching generally on these characteristics, but we're not doing an individual match by match by match. Okay. Now, matching on many variables may make it difficult to find an appropriate control. This makes sense, right? Especially individual matching. Also, this is kind of an interesting piece. We cannot explore the possible association of the disease with any variable on which the cases and controls have been matched, right? We already took care of that. We already made it set. So what if being a male makes you at higher risk for coronary heart disease? Well, if we matched on male, female, and non-binary in our groups, if we matched on gender in our groups, well, we can't assess for that. That's sort of not within our power anymore. They're already equal. Okay. This is a good one. Recall of information in a case control study. Yeah. So here you have to rely on people's memory of their past exposures, right? And sometimes this doesn't work out. Sometimes there's a recall bias. And this can occur when the recall is better among cases than controls because of the presence of the disease. So consequently, a false association may be found between exposure and disease. So this is a great example. Okay, so this is a study of maternal infections during pregnancy and congenital malformations. Okay, here's our cases. There's congenital malformations, controls, no malformations, okay? The true incidence of infection was 15% in both groups. But the cases, those who experienced the congenital malformation, 90% of them recalled the infection, whereas for the controls, only 10% recalled the infection. It's more likely, right? If you have an actual issue, you start looking backwards and thinking, was it this? Was it this? Was it this? You kind of go through it in your head. If nothing went wrong, maybe you never think it through and you don't remember. Okay, so that's a really important piece. Now, because of several limitations in the selection of controls, the use of multiple control groups may address some of the concerns. So you can use both living controls and dead controls. You can, in which case you're using surrogates to provide data for the dead controls at least. With hospital controls and community controls, hospital controls may have some conditions that lead to frequent hospital visits. So community controls helps offset that a little bit. Non-disease controls and cancer controls. Again, that recall issue, recall of past exposure might differ with the outcome. So if findings are in agreement between your different control groups, they're more likely to be valid. So if you find the same thing across these different control groups, you're in pretty good shape. So in a case control study of measles and subacute sclerosing panencephalitis, 2 control groups were used. Playmates of the patients and hospitalized patients in the same hospital. So you can see how these two are very different groups. And it might be helpful to see how their outcomes, how their exposure might have been the same in both of these, in these two very different groups. They were both matched on age, gender, and race, 2 cases. Okay. Nested case control study. Now, this is conducted within a defined cohort in which exposure data and the population characteristics are available to some extent, often from the time of enrollment into the cohort. Okay, so let's talk through this a little bit more. Okay, so both cases and controls are from a known defined population at risk of disease. Exposure data are collected prior to the diagnosis of the disease. So the information collected has not been influenced by the knowledge of disease status. Good, there's no interview or no information bias. And it's less costly than a cohort study because fewer subjects and fewer tests and or specimens are required. Again, this kind of almost sounds like a cohort study. So why are we calling it a nested case control? Again, think about the direction. Okay. Okay. Let's talk through an example that may help. In a study to determine whether the Helicobacter pylori infection was associated with the development of gastric cancer, 189 patients with gastric cancer and 189 cancer-free individuals were identified from 130,000 people from an HMO cohort followed from the 1960s. Okay, so this infection status was determined using stored serum collected during the 1960s. The proportions of infection were 84% among gastric cancer cases and 61% among the controls. So we are still looking at the gastric cancer. We're still looking at the case control first, in a sense, and then going back and getting our exposure. But in this case, thankfully, the exposure was already collected. So we don't have that little bias going on. It was all, the serum's already there. Okay. All right. So next we're going to talk about cross-sectional studies. Okay, so let's continue on with cross-sectional studies. A cross-sectional study is an observational study in which exposure and disease are determined at the same point in time in a given population. Downside, the temporal time relationship between exposure and disease cannot be determined. Okay, so here's our population. We gather data on exposure and disease at the same time. And we have our 4 groups. Exposed have the disease, exposed do not have the disease, not exposed have the disease, not exposed do not have the disease. So let's talk about this a little bit more. What does a cross-sectional study do? It assesses the prevalence of exposure and or of diseases in the population, and it provides clues for further research into the etiology of diseases. Right? So we can't say the exposure, is definitely related to the disease. We can't say the disease is definitely related to the exposure. We're just looking at more of an association here. In other words, we're missing that time component. Okay. Okay. So when we're talking about quasi-experimental designs, which is what we've been talking about actually, quasi means sort of. Quasi-experiments have a control group, a treatment group or program group, and variables. Quasi-experiments do not have random assignment to groups. Okay, so a little review there of where we've been heading. Okay. So let's look at the non-equivalent groups design. And this is one of the most frequently used quasi-experimental designs. It looks just like a pre-test, post-test design, but it lacks random assignment to groups. As a result, the treatment and control groups may be different at the study start, and it raises a selection threat to internal validity. So here's our non-exposed groups. Here's our observation. Treatment or program or whatever you like. And here's our observation again. Okay. So how can we potentially reach a cause and effect conclusion with a non-experimental group design? Okay. So, or excuse me, the non-equivalent groups design. Okay, my screen just went blank. Okay, it went blank again. Sorry about this, guys. Okay. So let's continue talking about the non-equivalent groups design. So we select 8 nursing home wards, and our N equals 300 nursing staff. Our intervention group is 4 wards, N equals 150. Our comparison group is 4 wards, N equals 150. Baseline survey for both, interventions for one group, follow-up survey at 12 months for both groups, follow-up survey at 24 months for both groups. Here is our pre-test and post-test means. Here's a different possible outcome. And yet another possible outcome. So let's go through these real quick, actually. Let's just make sure we're clear. So with the comparison group, nothing happens. And the program group, we have an increase, which we'll assume is positive news, good news, exactly what we want from the program. Here, even the comparison group is increasing, but not as much as the program group. So what's this due to? Could be due to trying to make the experimenters happy by reporting better results at post-test, something to do with testing, something to do with instrumentation, could be any of those. And here in this case, nothing happens with the comparison group, but the program group goes way down. So that's not what we want to see necessarily. Okay. And for this one, now this is a truly interesting one, right? Our comparison group stayed stable. Our experimental group increased a whole bunch, but they started at such a deficit. Now that's tough because who knows what would have happened had they started here. Would they have shown such an increase? We don't really know. Some would adjust for this in, this baseline and say, oh, well, it was clearly effective. I wouldn't be so quick to do that. Okay. And here, the comparison group, again, stays stable. With the program group, they start below the comparison group and then end above it. At least this is a little more clear because they're not way down and they did end above the other group. So it's a little more clear. Okay. So let's talk a little bit about the regression discontinuity design. A pre-test, post-test program comparison group quasi-experimental design in which a cutoff criterion on the pre-program measure is the method of assignment to a group. Okay. So let's look at the notation here. Now, C indicates that groups are assigned by means of a cutoff score on the pre-measure. And O stands for the administration of a measure to a group. X depicts the implementation of a program, and each group is on a single line. So we're kind of used to this. This is the only part that's really new is the cutoff piece. So we have them going to different groups depending on their cutoff. This group gets the program, OXO. This group does not, OO. Okay. So let's look at this. Here we have our cutoff. Here we have our regression line. And then here, let's look at the pretest. Here's our treatment group our would-be control group lying beneath that because it didn't hit the cutoff. So let's look at this a little bit more. How does the role of comparison group work in RD designs? If this is our treatment group regression line and this is our control group regression line, the reason it's called regression discontinuity is because we are looking for this discontinuity in the regression lines. That's what we're hoping for, right? Because we want to see that there is a difference in the effects. Okay. So in principle then, this design is as strong an internal validity as its randomized experimental alternatives. But in practice, the validity of the RD design depends directly on how well you can model the true pre-post relationship, which is a statistical challenge for sure, right? Trying to work that out is really a challenge. I think it's an interesting design. It's an interesting approach. I don't want you to take away too much about this one. I mean, it's cool if you ever want to try it for sure, but I mainly just want you to understand that we are looking for the discontinuity in the regression lines at the cutoff to really understand and show if there's a treatment. Okay. And just the basics of our notation here, how it works. Okay. All right. So this part's kind of interesting too. To achieve the same level of statistical accuracy, an RD design needs as much as 2.7 times the participants as a randomized experiment. So if a randomized experiment needs 100 participants to achieve a certain level of power, let's say 80%, the RD design might need as many as 275. So if you're wondering why you've never seen, or maybe you have seen, but if you haven't seen or only seen a few RD designs in your background of literature reviews, this may be why, okay? Because it does require so much more to get the same power. And yeah, and if you can randomize, it's really a great way to go. But if you can't, and you really want to show a strong internal validity, you really want to show this kind of this kind of power that this design has, you can do it if you can get the participants. Okay. The other piece is that RD designs tend to be more ethical because those who need a program or treatment the most can receive it. Right? Because that's probably the ones you're giving the treatment to. When you did your initial cutoff, the ones who came up higher on depressive symptomatology are getting your treatment as compared to those who came out lower. Okay. All right. Proxy pretest design. A post-only design in which after the fact a pretest measure is constructed from pre-existing data. Now, this is usually done to make up for the fact that the researcher did not include a true post-test. So not really the way you would love to go, but sometimes it's possible to get some information this way. Sometimes it's not possible to do a pretest, right? A pretest might just give them too much information about what you're studying, might give them too much testing practice. I mean, there are legitimate reasons why you might not be able to include a true p-test. So maybe you can make up for it a little bit by doing something afterwards, looking backwards. Okay. I wanted to give you a quick example of this one actually before we move on. So let's say you are doing some sort of cognitive measure at time 2. And maybe you might look back and look at an IQ test that you had access to from many years ago. Okay, so again, you might look backwards into the record, into the history, and be able to pull that out from pre-existing data on them. Okay, all right, so that's just one possibility. Okay, next. The separate pre-post samples design. This is a design in which people who receive the pre-test are not the same people as who take the post-test. Okay. So we've got two groups who receive the pre-test, two groups who receive the post-test. The one who gets the treatment also gets the post-test, but notice how these don't match up. Okay. And the double pre-test design, a design that includes two waves of measurement prior to the program. This is kind of cool because it can address maturation, and particularly selection maturation threats, because if there's going to be something that happens between here and here, between the first two O's, you'll catch it. So then we can worry a little bit less if we can assume the distance, or if we can assume what happens between the first O and the second O. Let's do the bottom group. From the first O and the second O, and between the second O and the third O, it's going to be relatively the same. We can account and address that. And then we can ascribe more of what happens to the treatment. Okay. Okay. Oops. Okay. The switching replications design. Now, we actually talked a little bit about this one already. So let's just review it real quick. This is a two-group design in which the two phases defined by three waves of measurement. In the repetition of the treatment, the two groups switch roles. So the original control group in phase 1 becomes the treatment group in phase 2, whereas the original treatment group acts as the control. So you have your O's here, treatment, O's here again, treatment, O's here again, right? So first time the top group gets the treatment, second time the bottom group gets the treatment. Bear in mind, these are N's. They could be R's, right? We could have this same study with R's here, randomly assigned. Okay. Oh, yes, the non-equivalent dependent variables design, or the NEDV design. Now, at first, this kind of looks like a weak design, but pattern matching gives researchers a powerful tool for assessing causality. So you look at the degree of correspondence between two data items. So let's look at this. We have completely no random assignment to groups. We have our measurement O1 x O1 and O2 O2. So it looks pretty weak because not the same measurements, right? But if we look at pattern matching, it can be helpful. So let's look at this. In our first group, we're looking at algebra, let's say. In our second group, we're going to look at geometry. Algebra group got the intervention, geometry group did not. Maybe we can do something with that. Let's talk about this one. The regression point displacement design. This is a pre-post quasi-experimental research design where the treatment is given to only one unit in the sample, with all remaining units acting as controls. Now, this design is particularly useful to study the effects of community-level interventions. So that's where you want to think about this, right? So we're going to do a major awareness campaign about COVID vaccines. We're going to hit hard one community, let's call it a particular town or city. And surrounding cities will not get the intervention. All the remaining surrounding cities do not get the intervention. So we can see by comparing the one city that gets the intervention to the surrounding cities that don't, if there is an impact, if it's worth now getting this intervention out to other communities at large. Okay. And we can look at some analysis. It's usually analyzed with an ANCOVA. Okay, so here we're looking at HIV rates. Okay, so let's assume we did some kind of community intervention. Again, an educational intervention. Here's our regression line. Here's our pre-test down here, our post-test over here. And this is our treated community point right down here, our post-test displacement. So let me put it another way, because I think this is actually quite confusing when you look at it with a regression line like this. Let's say we're analyzing this with an ANCOVA, right? Okay, let me go back. We're going to analyze this with an ANCOVA. So we're going to go ahead and have as our two groups Philadelphia and surrounding cities. Okay, we'll pick a couple surrounding cities that you like. We'll call those, or several surrounding cities, I should really say, that you like. We'll call those this group. They get the intervention. They don't. We're going to compare while controlling for the pre-measure, right? It's really repeated measures, ANCOVA, how they perform. And that's really all we want to know about that. All right. Okay. So then finally, we come to a non-experimental or correlational design. Okay, and this goes back to the beginning again. Is random assignment used? Yes, randomized or true experiment. If no, is there a control group or multiple measures? Yes, quasi-experiment. No, non-experiment. So perfect example of this. Let's just look at age and IQ. Both nice continuous measures. We can look at a correlation between the two. As age increases, does IQ increase? No intervention here, no control group. We're just looking at the association between two things. Nothing wrong with it. Perfectly valid study to perform, but it is a non-experiment. Okay. So let me pause here. Let me just say that that's a fair amount to take in, especially a lot of those last few designs I kind of put your way. I really just want you to have the basic understanding of how those designs work. And I don't expect you to ever do analysis with any of those designs. I think that would get a bit complex. If you just have a basic understanding of how they work, I think that's perfectly fine. With the most important ones, of course, being the first few we talked about, right? The cohort, the case control, the cross-sectional, and this, of course, is correlational. But those other few, basic understanding. We'll talk more about this as we go forward, and be well, stay safe. I'll see you next time.